Good morning, good afternoon, wherever you are in the world. Welcome to the Romax Technology Optimizing Bevel and Hypoid Gear Design for Automotive Axles webinar. Thank you for joining. I'm Rahini Sayo, Romax Marketing Campaign Manager, and our presenters today are Dr. Chris House, Head of Engineering Services, Romax Technology, and Dr. Marcus Brum, Technology Center Machines Tools Manager, KlingeInberg. The presentation today will last approximately 35 minutes with a 10-minute Q&A session. Before we get started, I'll just give a bit of background of Romax Technology. We're a leading global provider of integrated software and services for gearbox, bearings, and driveline systems for the automotive, aerospace, bearings, off-road, rail, marine, and wind industries. For over 26 years, we've provided consultant engineering support services. Our revolutionary software tools are Romax Designer, Concept, CAD Fusion, and Dynamic Fusion. Our drivetrain design analysis software tools are used by 14 of the top 15 automotive OEMs. Our right first time approach is used to solve engineering and process challenges you face and to accelerate your design and development cycles. Customers can achieve concept, detailed design analysis, validation, testing, and measurable and sustainable end-to-end process improvements. Let's get started. I'll now hand over to Chris and Marcus, who will give you a full overview of optimizing bevel and hypoid gear design for automotive axles. Marcus will be presenting the first part of the presentation, and Chris will be presenting the second part of the presentation.
Hello everybody. I'd like to give you a first presentation about the optimization of hypoid gears. We are faced with the megatrend that we have the challenge to find solutions to avoid the climate change. Therefore, we have to develop efficient axles with the requirement for low fuel consumption. Therefore, we have to design bevel gearboxes with a lightweight housing made of aluminum, and in combination, we have to do gear design with a low hypoid offset to reduce the friction due to the sliding speed on the flank. The reduced sliding speed has the effect that we have also a reduced contact ratio, what will increase the excitation of the gearbox, and so we have to find a solution where we can live with the higher deflections in the application, and on the other side where we can have an efficient design that avoids any excitation of the environment because the damping of the aluminum housing is lower. So what we need, a requirement for modern gear design, is having the lowest possible excitation considering the deflections of an aluminum housing. The higher challenge of an aluminum housing is that we have to live with a different temperature coefficient. That means that the axle is growing under temperature of operation, and this higher growth of this aluminum housing in opposites to the iron components in the like the pinion, the gear, or the bearings, this will lead to a reduced preload on the bearings, and in combination with a higher deformation due to the growth of the axle and the lower preload of the bearings, we see that we have to live with higher deflections in application. So what we need and what we will discuss during our presentation is how we can compensate that with an efficient approach to design the gears under consideration of the deflections in the environment. With an approach in combination with a KEMOS as a solution to develop the ease off, for example, and with a Romax Designer that is then necessary to have an efficient way to calculate the environment and the deflections under load. If you look at our standard process in KEMOS, KEMOS is made to simulate the whole process chain of manufacturing of bevel gears. We can predict based on our manufacturing simulation the geometry of the gear set, and we can then calculate the excitation behavior of this gear set based on the manufacturing process. But what is still necessary is that at the end of the development process, we need a driver who is evaluating the noise of the transmission in the application and gives a feedback, what is shown here with the dashed arrow. So he evaluates finally the gear design, and based on that, we will then define characteristics and criteria for the next step of development. So it is still an iterative process where the test driver is a very important component. Why is that so? Because we have on the one side the chance to calculate in detail the geometry of the part, but we have still an uncertainty of the behavior of the housing and the environment in the car. We still need this procedure that the test driver is finally evaluating the gearbox. What is also very important in this process chain is to determine, for example, the contact pattern in real application to ensure that the deflection values that have been considered in the design phase are correct. If you look into the details of the gear design, and this is the structure of the following slides, we start generally with a dimensioning process where we define the macro geometry of the gear, like the module, like the tooth width, like the spiral angle, and so on. So this is the result of the dimensioning process. With this result, we start calculating the load carrying capacity based on ISO standard, ACMA standard, or DIN standard, and we get as a result the safety factors against failure. If the safety is high enough, we can then go to the next step. If the safety for failure is too low, we have to jump one step back and we have to change the dimensioning for the macro geometry. So this is a first iterative loop. Next step is, after we have checked the load carrying capacity, is to optimize the ease-off design to ensure a good running behavior and a good noise behavior. Additionally to that, we have then the chance to use the loaded TCA to analyze the stresses and the local pressure on the flanks to ensure that we have also a good microgeometry that ensures high efficiency in one step, or on the other side also a good scuffing behavior and so on. So this is both also an iterative process. If after the ease-off design the stress values on the flanks are too high, we have to go one step back. We have to optimize the ease-off to avoid any failures on the flank. And I will give you an example how this works for a synthetic example that we have created. And this example is shown here. We start with the dimensioning step in the process. We have here an example with a gear set with 12 teeth at the pinion and 35 teeth at the gear. The hypoid offset is in the range of 20 millimeters. We have an outside pitch diameter of 200 millimeters, a face width of 38.4 millimeter at the pinion, and a normal module in the range of 4 millimeters. For this gear set, we have to design later the ease-off and the stress analysis. The load carrying capacity is something that I skipped in this presentation. The challenge in the design phase of the ease-off is that we have to live with deflection values. What you can see here, we have two variants. Variant 1 is the deflection for the drive side, and the variant 2 is the deflection value for the coast drive. For these both values, we see what happens to the contact pattern. We see here that the contact pattern moves from the center position more or less due to the deflection of variant 1 to the heel, and we see that the deflection for the variant 2 moves to the toe. And we have to find an ease-off that is on the one side robust against these deflections here of the contact pattern, and on the other side we have to ensure that we have a low excitation behavior in general so that we have low noise. The next example is now for this gear set that I've introduced 2 slides ago. We see here the standard is off for the starting point of the optimization. We see that we have a contact pattern on the concave flank near the toe, and we see also that we have a centered contact pattern for the convex flank here. We see that we have a transmission error in the range of 47.4 microradians, and if we apply the deflection that we have considered for this design, we see here we have a change in the hypoid offset for the drive side. It is reduced, and what we see here, we have similar transmission error for this application. And when we look in the coast flank and the other value for variant 2, we see also that we have only a slightly different change in the transmission error. But in general, due to the experience from the driving, we see that the noise behavior of this transmission is too high, and we have figured out that a good running behavior can be ensured if we have a transmission error in the range of 25 microradians. So what we did is we had to reduce the crowning to ensure that we get a bigger or a smaller transmission error. What is shown on next slide, we have reduced the lengthwise crowning and reduced a little bit also the profile crowning, and with this effect we could increase the size of the contact pattern and we could reduce the excitation behavior. But if we consider the deflections on the load, we see here that the robustness of the position of the contact pattern was bad compared to the first version. We see here that we have an increase of the transmission error from 20 microradians up to 67 microradians. So we had a 3 times as high as transmission error, and this is then a problem for the running behavior in this position. And also we have edge contact at this position, and this is also bad for the load carrying capacity of this gear set. So what we had to do is we had to find an optimized crowning, what we achieved with an additional higher order modification by applying also a higher twist. And what we see here, we have at standard position, we have here a transmission error in the range of 12.3 microradians. And if we apply the deflections, we see here that we still keep lower than 20 microradians for the drive side. But the excitation behavior is just one thing we have to take into account. Last but not least, we have also to ensure that we have a good stress behavior. We see here for this design that we have made before, we have a maximum Hertzian pressure in the range of 1000 megapascal, and our aim is to reduce this furthermore to have the chance to apply higher loads on this gear set. Therefore, we can also check other values like the tooth root stress. For this design, we see here a maximum stress in the tooth root at the range of 260 megapascals. And we have this for the pinion concave flank, and we have this also for the gear convex flank. So these values are almost similar. We can also see the transmission error under load, and we can also see the fluctuation of the stiffness here as a result from the loaded TCA. Now we have applied locally different crowning. We see here that we have in the area of the toe lower crowning. Here in the range, in the area of the heel, we increased the distance of these off to have on the one side a low excitation behavior, lower than 25 microradians in the nominal position, and under loads we see then that we still can keep the good deflection behavior. And what we also can say, due to the reduced crowning here in this area, we can reduce the local stresses at this area. This is shown over here. We could reduce the maximum stress by 50 megapascal, and see that we have then the chance also to improve the load carrying capacity of this gear set just by optimizing the ease off. Here you can also see that this had a more or less normal effect on the tooth root stress. The tooth root stress level has been kept similar, and also the stiffness fluctuation has been similar to the example before. Very important is for an optimal ease off is that this is then designed for certain values of deflections, because we want to make the best possible solution. So we need an ease off that is shaped for a certain deflection, and therefore it is very important to determine these deflection values. In my career as a researcher, I made investigations of deflections under load in gearboxes, and you see here a typical test setup to determine the deflection values in a real application. What you see here is that you need 10 sensors to determine the pitch or the position of the pinion and the position of the gear in the application under load. And if you would use this approach to optimize a gearbox with different design status, you have to make always a prototype. You have always to repeat this big effort to measure the deflection under load and under temperature. And this is not an efficient process for an efficient design. You see here the need why we have to calculate, for example, the load influence on the deflection values. You see here just some general charts for the change of the hypoid mounting distance and the hypoid offset, for example, and the pinion mounting distance. And additionally, you see also the influence of the temperature. We started at 30 degrees, raised the temperature up to 70 degrees C, what is still not the maximum that is usually occurring in a real application. And so you see that we have big ranges of variations, and therefore we have to find an efficient approach to simulate that. And so I want to sum up my first part of this presentation. You have seen that there is a chance to optimize the load or the load carrying capacity and the excitation behavior if you know the real deflection values. Therefore, you can use higher order modifications of the ease off. But it is very important to have an efficient way to determine these deflection values. And from our point of view, the Romex Designer, what Chris will introduce to you, is an efficient tool to calculate these deflection values. I thank you for your attention.
Thank you very much, Marcus, for that very detailed analysis of designing hypoid gears for automotive axles. So as Marcus says, I will now look at the side of the problem which is predicting the deflections. So understanding the system and understanding the variability is essential for coming up with a robust design. So you could do trade-offs like looking at the housing deformation, whether the housing needs to be stiffer versus can you cope with the deflections with gear modifications. And of course, we'll want consistent performance of final products in mass production, for instance, from the point of view of gear wine. In terms of sources of the system variability, of course, the contact patch will move under load, the assembly preload, temperature differentials between the housing and the shafts, geometric tolerances, particularly bearing bore positions, and even the differential carrier rotational position. These can all affect the misalignment of the hypoid gear set and therefore the position of the contact patch. So many people modeling axles use standard FEA solutions, but these have quite a long solve time and not really suitable for doing very quick design iterations. And really standard FEA is not the best way for modeling gear contact and bearing contact. But maybe those solutions are okay for doing a design validation once you've created a design. However, the Romex Designer with KEMOS permits rapid concept evaluation, and this enables you to quickly come up with designs that then you can evaluate. And the reason it's much quicker than a standard FEA approach is because Romax includes semi-analytical models of bearing contact mechanics rather than trying to mesh very finely in the contact area. It includes super element reductions for complicated structures such as the diff carrier or the housing. And then, of course, by using all the strengths of KEMOS for the design and analysis tools, we can come up with a good bevel and hypoid design. I've got some images here from the Romax Designer software of a very simple model. This is actually a Romax Designer example file. So that's an FE mesh of the differential carrier. That's imported into the Romax Designer model, where we can then add all the bearings, standard shafts, and the gears. The gears can be generated by using a KEMOS KIP file. We can also model the straight bevel gears as simple elements. That Romax Designer model, the first thing it can do is predict the static deflections of the system, as shown there. So that includes all the 6 directions of motion. And from the loads on complex structures, you can get the stress on those components. You can look at that in more detail in third-party tools if you so wish. So animation from a simple model here. Just to recap, diff carrier, for example, model with meshed FE, which is then condensed to a stiffness matrix. The differential straight bevel is a model with beam elements typically. So we're not typically analysing them in the same level of detail as the hypoid gears because they're not operating continuously. The Romax bearing models include clearance, misalignment, and have non-linear contact stiffness. I'll come back to the bearing models on the next slide. Gearbox housings can be included. There's one in this model, it's just hidden. And those housing models can be imported as CAD or meshed FE and then reduced to stiffness matrix between the connection points. Simple shafts can be modeled with Timoshenko beam elements or can be meshed as solid meshed FE components. And that allows you actually to also include flexibility of the bearing raceways and look at the effect of flexibility on the bearing load distribution. And hypoid gears designed in KEMOS using the interface between KEMOS and Romax Designer. So really the key part of this, where the Romax Designer system brings the biggest value in doing this axle design, is really enables to get non-linear bearing analysis. And that enables you to get the correct misalignments. And that includes the clearance or preload, includes the effects of how fit of the bearing rings will change the internal clearance of the bearings, including the model thermal expansion effects. So if you can estimate the temperatures of different components, then that will change the axial and radial positions of the bearing rings and hence the load on the bearing. The Romax model also includes all the roller modifications. These can be estimated if they're unknown. Often bearing companies won't share all the details, but Romax will back estimate typical roller modifications with a logarithmic profile for taper or cylindrical bearings. Got a few images from the software. So that shows all the parameters that are used to define the macro geometry of a bearing for a taper bearing. You can see it's defined in quite some detail. And then once you've selected your bearing or designed your bearing, you can then assemble it onto a shaft like this. And this is a pinion shaft showing the bearing position and the position of the gear. And when Romax does the static analysis, for shafts, it constructs the shear force, bending moment, and then stress diagrams, as you would from textbooks, but it's doing this, including the bearing nonlinear stiffness, and simultaneously solving with the stiffness matrices and the gear load. And it calculates the bearing load distribution. That shows the stress on the rollers. You see the load has been pushed towards the bottom left in that picture, and the rollers in the bottom left quadrant are all loaded. That graph shows the peak stress. This graph shows the stress distribution along the length of the rollers. So here you can see there's a slight misalignment because the load is pushed more to the right of the image. And also, it will calculate the film thickness, which is important for understanding the life and the lubricant selection for the axle. And on this image, you can see that those load distributions superimposed on top of images of the bearing rollers, which is convenient for checking that the model is behaving as you expect in terms of the directions of loads. So as Marcus described, really you can reduce the hypoid gear mesh misalignment into these 4 parameters of various different names, but really it's the shaft positions relative to each other and the offset. So a few days ago, when I was preparing for this webinar, I used the Romax example file to generate a few graphs showing sensitivity studies. For instance, showing how the misalignment can vary with torque. So I ran a case running from 200 to 1200 Newton meters, and you can see how the misalignments are varying over that range. So that means that your contact patch has to cope with those ranges of misalignment. Another study was looking at the bearing preload. So the preload could be varying in your design for when you are looking for what value to select, and that would be a trade-off of stiffness and bearing life. Or it could be you are looking at the variation that occurs due to assembly variation, so the tolerance you're having when you're assembling these on the production line. A further example I did here was looking at in the pinion head bearing outer ring. So this is assuming there was some tolerance on the housing between the 2 bearing mounting positions, and you can see that is also going to affect the misalignment of the gears. Also, the differential carrier rotation in this simple case, you can see that as the differential carrier rotates, the x-axis is the rotational position. You can see there's some variation in the misalignments, particularly in the shaft angle between the pinion and wheel shafts. So all these graphs are quite quick to generate, and this really gives you a deep understanding of the variations that you're likely to encounter due to manufacturing error, due to loads in operation, and so forth. And by using this, you can then take these inputs into KEMOS to understand where the contact patch is moving to. So that's the kind of technical output from the software. But really the reason for doing this is to increase efficiency of the design process. And we want to provide the tools to help make the right decisions early and avoid rework and minimize the number of prototype iterations. So this Romax designer working in parallel with KEMOS and as used to do rapid sizing of gears, bearings, shafts, and housing, and this might be useful to respond to commercial needs. And then with the tools that Romax Designer have developed, the system computer-aided engineering model allows very rapid evaluation of design changes in any of the components for any, like the carrier, housing, or bearings. You can quickly re-import a design change or change it within the system and model itself, and then see the effect on all the inputs and outputs, like I've shown here. So you can change the bearing selection. You can look at lightweighting the housing. You can look at the hypoid gear ease off. Look at the changing of the lubricant type. Look at temperatures. And then the model gives you all these outputs. The model between Romax and KEMOS gives you gear life, efficiency, transmission error, bearing, stress, life, efficiency, the housing and diff carrier loads from which you can determine the stress. And then you can also use the Romax Designer model with transmission error output from KEMOS to look at the system vibration response and therefore get a good understanding of gear whine. One particular area I'd like to highlight is the Romax solution for officially integrating with your CAD process. So we developed a piece of software called CAD Fusion, and our latest release delivers a major step forward in modeling and analysis productivity when using Romax Designer tools. So it allows not only the translating into Romax, but also the creation, modification, and then the meshing of 3D components. And this reduces the need for third-party CAD and FEA packages. So without the need for third-party CAD and FEA packages all the time. So the aim is here to enable the Romax Designer user to be able to make design modifications to things like housings or diff carriers to do design investigations without having to maybe go to someone who's in another department to get that modification made. So this means that the components can be created very early in the design process, and then, as I say, meshed within Romax Designer. And so this ribbon on the bottom is the tool set from the CAD Fusion, and we can see there's now new 2D sketch tools for creating revolve shapes. There's a blend tool, and there's tools for creating different patterns. A further step where we've tried to help axle manufacturers improve efficiency of their process is by providing special tools for embedding their own expertise within their design process. This is because hypoid gear specialists typically have limited availability within their companies, and development times are always squeezed. And often we found a requirement that non-gear experts need specific results or need to evaluate particular design changes. For instance, looking at changing the wall thickness on housing, looking at effectively a different bearing choice. We might be able to well enough define those individual tasks that we can use them with a separate application to run Romax Designer in a server listening-based operation. So by creating template models that embed the expertise of your gear experts, you can then free up them by allowing other people to quickly access those models to do specific results or do specific design changes. So we're working with quite a few people in different areas, looking at customizing particular tools for these types of actions. And those tools can be written in-house, so it's an open interface that can be run even from Microsoft Excel, or we doing work on customizing these kind of tools, or other third parties can as well. So we're looking to embed this Romax and KEMOS process within the design process. And systems like Comet Solutions or Dassault EyeSight can then be used to run Romax. So in summary, as Marcus has described, KEMOS is the best tool for the design and analysis of bevel and hypoid gear pairs. So really have to emphasize the design side, this particular power. And then accurate information about gear misalignments is needed to then get an accurate prediction of the contact patch and the transmission error. The Romax Designer models include complete gearbox systems, including the housings and thermal expansions. And then deflections of all those components can be taken into account to calculate the mesh misalignments, and KEMOS can then be used to refine the gear contact. And we've worked hard with KlingeInberg to make sure that process is as seamless as possible. So we have a very close integration between KEMOS and Romax. Romax can read a KIP file to generate a Romax gear, automatically outputs the input instructions to KEMOS, and then automatically reads the transmission error for doing system vibration. So thank you very much for listening.
Thank you very much, Chris and Marcus. I hope you found our presentation useful and informative. Now let's begin our Q&A session. Chris and Marcus will now answer your questions. Thank you for sending them in.
I'll answer one. There's, with Romax, is it possible to generate a housing stiffness matrix without an FEA program? So yes, it is for most structures. The CAD Fusion package, which is effectively a module of Romax Designer, has the capability for creating, modifying and meshing housings. Doesn't have the same level of capability as a dedicated CAD or FEA package. For instance, you can't very easily refine the mesh in one area and have a different size mesh somewhere else. So, but it gives you some capability that we think is really beneficial for improving the speed of operation.
Okay, there's one question in the optimization of ease-off problem. Are the EPG and alpha displacement imposed? So at KlingeInberg, we call it HJV and sigma, but at this end, we can also calculate EPG and alpha values or consider them that it's just a configuration of the program.
I think Niranjan is asking about whether they are imposed. I guess they are calculated by Romax Designer and then transmitted to KEMOS.
Yeah. The benefit of this interface between Romax and KEMOS is that there is no problem to interpret the failures. So we have conversion. So if the values are calculated in Romax, we can then consider them directly to optimize the ease-off. So the deflections coming from Romax Designer can be directly considered in the ease-off optimization.
I've got one about, in Romax Designer, how can the stiffness of the differential carrier as a function of ring gear rotation be captured? In the models, as the diff carrier finite elements have to be mounted in the desired position. No, you can rotate it to different positions. So Romax, in those graphs I showed, Romax was doing multiple static analysis. So moving the carrier to a discrete new position, then moving it again, then moving it again.
Yeah, and then additionally one question, how the gearing is defined in the software, how is the input? So we generally define in the first step the geometry of the gear set in KMOS, and then we load this data into the Romex Designer model.
There's one about gear body flex in the calculation. So in Romax, if you have a gear body meshed as a finite element component, like that differential carrier in the example, then the load is applied at a point on the gear face width, and so any deformations of the gear blank would be included. They would be captured by the deformation of these FE components.
Yeah. And there's one question coming up: if the use of a defined gear geometry make the deflection calculation more accurate. What we do is that we have a chance to recalculate also the deflection values as an iterative process based on a certain ease off. So we see that in certain conditions we have a better calculation also of the deflection values if we consider the correct ease off for the deflection calculation.
There's another one about the diff cage and orientation. It's reduced to a stiffness matrix, but the stiffness matrix is not necessarily rotationally symmetric. So if there's windows in the diff cage, it will be not symmetric and therefore can be rotated to different positions.
There was one question if it is possible to make completely free-form ease-off designs. What you can do in general is, firstly, is each ease-off design is based on the neutral data format, so we simulate bevel gear machine to generate the ease-off. If you want to consider a free-form design, you can also load or use the interface for measured topographies and load that into KMOS in case you want to be completely in free form. If you do this, you can then also use the calculated ease off as a template, and later on you can try to optimize the manufacturing process to get as close as possible to this, as you say, free form design. And we see generally that we have almost the right degree of freedom to achieve almost all free-form designs that might be possible.
And there's a question about mesh forces in Romax based on nominal pitch diameter and spiral angle. So at the moment, Romax makes the assumption that the load is transmitted at halfway down the face width, so sort of a nominal point. I think for the future, we'll look at whether we can do the iterations to understand if the load is transmitted more in the center of the contact patch that might be not very close to the center of the face width. But at the moment, it's the center of the face width.
And then there's a question what kind of material coefficients we use when we do a loaded TCA. What we do is with the loaded TCA, we consider the general E module of iron, and the hardness of the material itself has, in our experience, only a little influence on the deformation and on the E modulus, and so we don't consider the surface hardness or the loaded TCA calculation.
And there's one about correlation. So I think I was actually earlier looking at some work we did a long time ago where we showed some correlation of misalignment against predicted deflections. In Romax, there's a Gear Solutions article I think you can look up, and shows one example. So I think we get pretty good correlation, definitely good enough to make good design decisions. And there's one about complex temperature distributions in the housings and shafts. You can define a vector for the motion of each of the points in the stiffness matrix. And at the moment, Romax will only calculate those for a constant temperature in any one FE component. I've never actually done this, but you could work around that and scale those directions if you had a solution from another tool. I think that's another thing that we'll be looking at in the future to develop, is having a temperature gradient within components. There's one correlation question about loaded contact pattern or EPG. We've done the correlation against measuring shaft deflections in a setup similar to the one Marcus showed on his slide. We also very frequently are getting good contact patch correlation in project work that we do.
That's one question regarding residual stress level you recommend. In general, the residual stress level is a result from two aspects. First is the heat treatment process itself, and on the other side, we see also that we have little influences on the residual stress after manufacturing. If you grind gears, you see that due to the grinding process, you can have a little increase of the residual stress in the surface area. What the optimal stress level is not a general question that is easy to answer. In Germany, we have a research association what investigates the optimal residual stress since years, and depending on the failure mechanism, it depends. So there's no general answer from my opinion what we can give.
There's another question about correlation. So I've not specifically done correlation on thermal effects. Of course, you can keep on trying to do more and more correlation. But really, my feeling with correlation is you want to get a good correlation with your model so you can then use the model with more confidence to make predictions. Modeling time comparison between Romax and FE. There's a question about what is your comment about modeling time comparison between Romax and FEA. So obviously it depends very heavily on the level of detail in your FEA model. My experience is that a quite detailed model of FEA could be solving in the order of hours, whereas a Romax model solves in seconds, if not seconds, then within a couple of minutes.
The surface hardness after grinding should be in the range of 58 HRC, so Rockwell hardness. Okay, so I think maybe we'll wrap up there. As Rahini's just said, we'll send the webinar recording to all webinar registrations and attendees.
Unfortunately, that's all the time we have right now, but Chris and Marcus will answer any remaining questions by email. If you have any questions on this webinar topic or require further information, please email marketing@romaxtech.com and we'll get back to you as soon as possible. For more information on our upcoming webinars and on our on-demand webinars, please visit the webinar section on our website. We have our introduction to gear failure mechanisms and design optimization and practical aspects of gear and gearbox design webinars available to watch. And we've also got another webinar next week, a practical analytical approach to solving gearbox failures, next Wednesday, 16th of December, 8 AM and 4 PM GMT time. We'll also be sending out e-shots with more information shortly. We hope you will join one of our future sessions. Thank you and goodbye.